So this is the last presentation. So just as the last video of all the prototypes and everything that you have seen, and this is what we were referring to earlier, that Kent asked if I was going to show it, so here it is. You have seen how Michael had been working and his team like on a three-wheeler. So Kent had this idea of doing something in between that and a bicycle. So that's how we designed this three-wheeler. That is a three-wheeler when it's driving autonomously. And also Michael mentioned like this idea of vehicles that have three wheels are stable, whereas with two wheels, vehicles are not stable. So that led us to, for example, prototype this other vehicle. So I think an important part that you have seen throughout our presentations is that we are not saying specifically like the PEV or specifics or a bicycle should be like the solution for every city across the world, but it's more like this ecosystem of vehicles that are lightweight and autonomous that we're thinking about. And then the specific designs, if they have like 3 wheels, 4, they are covered, they have AC, cooling, could be like dependent on the specific city. So with that, I'll move on to showing you more of the simulation and modeling work that we have done. Because the idea is that in addition to modeling and prototyping these vehicles, we were also very interested in understanding what were like the fleet level implications. So one of the first studies that we did was to do a simulation study of the fleet performance of autonomous bicycles. And we did this study in Boston. So we took Boston's Blue Bikes data, and we had the question of saying like, okay, for this same demand, how many autonomous bicycles would we need? Our intuition is that we might need fewer, but we didn't know if that was true and how many less. So through modeling different scenarios in this simulation, we saw that actually with autonomous bicycles, you could reduce fleet sizes by 3.5 compared to current station-based systems and 8 times compared to current dockless systems. So we did see that actually like having vehicles that instead of staying where the last user left them, if they can go to meet up the next user, the system as a whole is much more efficient. And this order of magnitude is actually pretty large. And then, like, in addition to seeing like these more like high-level conclusions, we also saw like this kind of modeling allows you to have like very fine-grained analysis of what's going on in your fleet. So, for example, here we can see throughout the day for all the vehicles what they are doing. So, for example, at night most of them are stopped. Then you see in the morning like the peak hour when vehicles are like picking up someone or in use. After that rush hour, there is some vehicles that go for a recharge, and there is like a similar pattern in the afternoon. And this is for the overall fleet, but actually you could also see like these patterns for each individual vehicle of these 1,000 of vehicles because of how this type of modeling and simulation frameworks work. And then another interesting thing that we learned in these studies, and we will be playing like with the results of this simulation later in the exercise, is how different parameters correlate with each other. So for example, you could decide to have more vehicles. If you have more vehicles, your wait times are going to be lower, right? Or if your speed of the vehicle is higher, if they travel at 20 kilometers per hour instead of 1 kilometer per hour, the person that is waiting is going to wait less. So there is this kind of trade-offs that you can see very clearly in a simulation. So for example, I guess you could get insights like, if I want to have like, say like 1,000 vehicles, maybe it's worth it for me to design a vehicle that can go I don't know, like at 10 kilometers per hour, but maybe it's not worth it to go to up to 15 kilometers per hour, or maybe 15 but not 20, because here the difference in how the wait time decreases is very small. So there is like this kind of like high-level conclusions that we got. This is just an example, but we also saw like how battery size can have a different impact, how, for example, battery charging times also have a similar effect, and so on. So this is like different type of analysis that we have seen. And in particular, one of the conclusions that was very interesting to us is that conventional systems like Blue Bikes, for example, they are used around 2% of the time, whereas autonomous ones are used for over 8% of the time. So this is like a 4-fold increase, which is like a very high increase, and that's kind of like intuitively, that's why we need like 4 times fewer vehicles, more or less, rough numbers. But at the same time, this also means that there is still like this 92% of the time when the vehicles are not being used. As you saw like in the previous graph, there is like kind of like these peaks of demand. I think I have a video here. So whenever you have like your peak of demand, that determines like how many vehicles you need in your city. But then when people are at work, for example, or at night, of course, you have a lot of time when the vehicles are not being used. And this ties back to what, for example, Johnny mentioned of having like vehicles maybe do other tasks, or Michael mentioned also like having like the package delivery in the rear that can be cooled and so on. So building on top of that idea, like the concept is that, well, maybe the same vehicles that can do deliveries in the morning, they could transport food at lunchtime, they could transport packages in the afternoon, pick up trash. So there is like a lot of functions that could be, once that you have like the vehicles out there, you might as well use them for other tasks. So in a recent study that we worked on during the last year, we did a simulation similar to the one that I showed before, but that looks specifically at what happens if you have, instead of having a dedicated fleet for passengers and a dedicated fleet for food deliveries, if you have a combined fleet. And we did two case studies, one here in Cambridge and another one in San Sebastian, Spain, which is another one of the cities that we collaborate with. And we did see that you can reduce the fleet size by 15 to 20%, and think that this is just by combining two different types of demand. So overall in the city, like if by combining two types of demand, you could have like 20% fewer vehicles. You can imagine that if you added like other functionalities, you could even decrease the number of vehicles that you would have even further. So this is one of the studies that the type of analysis that we have done. Of course, this could be expanded, as I said, like by adding more functions, but you kind of get the idea of what we were discussing about in the previous presentations, but kind of like in the simulation world and trying to quantify the effect of that. And there is another leg of analyzing the implications of these systems that taps into the what you just were asking about, the environmental impacts. Because honestly, it could have been the case that you need like 3 times fewer vehicles, but you would still have a higher environmental impact. It could have been the case, right? So what we did is to do a life cycle assessment, which is a type of modeling that considers all the CO2 equivalent emissions that are from the extraction of the raw materials, manufacturing of the vehicles, transportation, use stage, up to the disposal. And what we saw is that you can actually reduce also the environmental impacts compared to current dockless and station-based systems. And I think I have the numbers here. So there is like different, like the manufacturing stage, delivery, and so on. But overall, I think the reductions were like 38 and 60%, more or less. And I think it's also important not to just see this like kind of like comparing autonomous bicycles to station-based and dockless systems. I think it's also important to see like how this compares to other current vehicle types. So for example, here you can see how autonomous vehicles compare, for example, to private e-bikes. It's still more efficient to use your own private e-bike, and of course it's much more efficient to walk. The emissions are way lower, as you might expect, than combustion engine cars, buses, and taxis, lower than electric cars. This is with a zero carbon grid, and it's like kind of like in the same ballpark as fully electric cars and fully electric buses and metro. So what kind of like this raised, at least for me personally, is the conclusion that if we are deploying these systems out there and the people using it are people who otherwise would have walked, we are not having a great impact on the environment. But if we get to have a mode shift, for example, from people that were driving and now start to use these autonomous bicycles, then the impact is like you do see a very high reduction in the environmental impacts. And that's actually like a piece of information that we are missing that we honestly don't know. And we are just starting like a new study where we are developing a survey where we are asking a large pool of people to tell us about a recent trip, and then we propose a series of alternative scenarios, and we see if people would switch or not. And this is an ongoing project, but what I wanted to ask all of you, this will be done after the class, but this is still work in progress. But I wanted to ask you to kind of like fill in the survey for yourselves, and then I will do like an analysis, even if it's like a small group of people. After the class, I'll do like a small analysis, and I'll give you like the results, and that will be actually like the first experiment, and we have no idea of what the results are going to look like, but I thought it might be like a fun thing to do.